when we were studying single variable calculus, we learned how important the chain rule was. Once we learned how to take derivatives, we learned when you have something like if you want to take derivative of a function, but it's really a function of another function, something like this, right? Then to be able to compute the derivative, we had to use the so-called chain rule. And the chain rule looked like this. It says you take the derivative of the exterior function and leave the inside function the same, and then times the derivative of the inside function, like this. And what we want to consider now is, since we're looking at functions of multiple variables, we want to say, well, what happens to the chain rule when we have functions of multiple variables, right? If we have something like, say, what if we wanted to find the derivative of a function now not of one variable, but of two? Like, let's say we had some function f of xy, but maybe x and y are functions of some other variable, t. And so we actually end up getting that f is a function of g, which is a function of t, and a function of h, which is a function of t. And so what we want to examine is a chain rule for functions of multiple variables with one independent variable. So let's start there. Chain rule for one independent variable. Okay. So suppose we have x, which is a function of t, and y, which is a function of t. Let's suppose that these are differentiable in t, meaning that x prime and y prime of t exist. Let's also suppose that z, which is f of xy, is differentiable in x and y. Well, then we can write z as a function of t by saying it's x of t comma y of t, right? And so if you substitute x for a function of t and you substitute y for a function of t, this becomes a single variable function in the independent variable t, right? And so we want to calculate dz dt. And if we calculate dz dt, we can do this by using the following multivariable chain rule for one independent variable. It says that dz dt is equal to the partial derivative of z with respect to x times dx dt plus partial z partial y times dy dt. And so this is the idea for the multivariable chain rule in one independent variable. So let's see an example right away. Or let's do a few examples. We have z equals 4x squared plus 3y squared, where x equals sine t and y equals cosine t. And so we want to find dz dt. Okay, well, we know that dz dt is partial z partial x times dx dt plus partial z partial y times dy dt. Okay, And so what we need to do now is compute all of these derivatives. So what is the partial derivative of z with respect to x? Well, we come up to the function for z, and we see that the partial derivative is going to be 8x, and then times dx dt. Well, the x is sine t, so the derivative of x with respect to t is going to be cosine t, plus dz dy, or del z del y, since it's partial derivative, right? And we see we'll get 6y times dy dt, which is going to be negative sine t. And this is a derivative with independent variable t. And because x and y both depend on t, it is important that we substitute x and y so that our answer is purely in the variable t. And so if we do this, we'll get 8 times x, which is sine t, times cosine t, and then minus 6, y is cosine, so cosine t sine t. And so it looks like the answer is going to be 2 sine t cosine t. And this is how we calculate dz dt for this given function, where x and y are also functions of a different variable. I want to make a quick remark here, is that you can substitute first and then take the derivative later. So what if we were to, let's kind of copy, we have z equals 4x squared plus 3y squared, right? And we know, what do we know? We know that x is sine t, so we have 4 times sine squared t, and then plus 3 times cosine squared t. Okay. Then what we could do is we did the substitution first, and now we take the derivatives, right? So what is dz dt? Because this is a single variable function, so it looks like we're going to get 8 sine t times cosine t by the chain rule, by the single variable chain rule, right? And then plus 6 cosine t times negative sine t, which is 2 sine t cosine t. And it's no mistake that this is the same. And the remark is that right now, while we're learning how to use the multivariable chain rule, this is the formula we should be using. But if you encounter a function in the wild, say, somewhere, right, and you want to take the derivative of it, and you need it's of variables that are dependent on another variable, in general, what you want to do is whichever method is easier, right? If it's easier or gives simpler differentiation by doing the multivariable chain rule, then that's absolutely the method you should use. If there's a situation where it's easier to substitute first, and then maybe if you substitute first, there's a lot of nice cancellations or something, and then so the derivative, taking the derivative is easier in this setting, right? And so for now, the functions we're working with are pretty convenient to do either. But it's worth a remark that it is no mistake that you'll get the same thing by substituting first or by using this multivariable chain rule. But I think in general, it's the factor of easiness with plugging in first changes once we start to look at more independent variables. Like once we get to like 2 or even 3 independent variables, or in the general case, then the probably most time effective route is to use your multivariable chain rule here. So let's do one more example while we're getting a good idea here. So let's let B, or example B, we have z equals root x squared minus y squared, where x equals e to the 2t and y equals e to the negative t. All right, and so we want to find dz dt, right? And so here you can see if you were to sub in x and y immediately, like if you were to write this as a single variable function, then the derivative's not that fun, right? And so what we can do instead is use our multivariable chain rule, which remember is partial z partial x times dx dt plus partial z, partial z partial y dy dt. And so let's see what we get using the multivariable chain rule. Well, dz or del z del x looks like it's going to be 1/2 square root, not square root, 1/2 x squared minus y squared to the negative 1/2, right, times 2x, and then that's times dx dt, which is 2e to the 2t. And then this plus partial z partial y, which is 1/2 x squared minus y squared to the negative 1/2 times negative 2y, and then times e to the negative t. So let's simplify this. Looks like it's going to be x times, so 2, this 2 cancels with this 2, but we still have a 2 left over. So it's 2x e to the 2t over root x squared minus y squared, right? And then you'll notice the second term has the same denominator, so we can go ahead and combine these denominators, and I'll get cancellation with this 2 and this 2, but I have minus y e to the negative t. That should be a minus in the denominator. And now I can plug in, this is not the 2 I wanted to cancel with, apologies. Let's cancel with the 2 in the denominator and not the 2 in the next line of the expression. And so now we can sub in x and y, and then we're done. So if we sub in x equals e to the 2t, so let's do that just by deleting our x's and our y's. Now we're subbing in x equals e to the 2t, so this was times e to the 2t, y was e to the negative t here, and then we have e to the 2t squared is e to the 4t, and then minus e to the negative t squared is e to the negative 2t. And if we simplify the top expression, we're going to get 2e to the 4t minus e to the negative 2t, right? So once we combine this term here, we get 2e to the 4t, and then we combine the product of these two exponential functions. And we know when you take the product of the exponential, you add the exponents, and it was negative t minus t, which is minus 2t. And so here is our the derivative dz dt using the multivariable chain rule, right? And if you'd like, you could go ahead and plug these in first, and then compute the single variable derivative. And there you'll have to use the single variable chain rule, and then you can verify that indeed we get the same thing. So there's a nice way for helping us remember the formula, and it's called a tree diagram. You know, we can have this formula memorized in single variable. It's not too bad, right? Once you write it down a few times, it starts to come by memory. But in general, when we start looking at functions of more than 2 or 1 variable, then memorizing the formula is not so easy or not worth our time even. So what we can do is we have a nice mnemonic device here of a tree diagram. So I'm going to draw some nodes on the screen here. And each node is going to represent one of our variables, right? And so when we were looking at z is a function of x and y, where x and y were both functions of t, we have 1, 2, 3, 4, 5, or 4 variables, right? We have z, we have x, we have y, and then we have the variable t, but I'm going to put it twice since it shows up twice, right? Once here, once here. And so now a branch in this tree diagram, so this is z equals f of xy, right? And this is x, maybe I'll write x equals x of t. A branch connecting the variable z to the variable x, we're going to indicate that this branch is the partial derivative of the top variable with respect to the bottom variable, right? So the top variable of this branch is z, the bottom variable is x. So it's dz dx, which means this branch here will be the partial derivative with respect to z, or partial derivative of z with respect to y, right? Because this is how we're indicating our branch here. And then what's the branch between x and t, right? Well, if this is, we're going from x to t, this is the derivative of x with respect to t. It's not partial here because it's a single variable, right? And we have the similar picture on the right side. The branch from y to t will indicate by dy dt. And now what we can do is say dz dt, dz dt is equal to, and then we can take the product. We can start at the top of the tree, and we can follow all the branches on the left. If we follow the branches on the left, we get dz dx is the first branch we travel along, and then the next branch we travel along is dx dt. And then we can do the same thing. If we start back at the top of the tree, we go down the branch on the right side, we travel along partial z, partial y, and then we travel down the second branch of this section of the tree, and the second branch was dy dt. And now if you take the sum of all the separate paths you took, you get precisely the multivariable chain rule. And so we can use this tree diagram to replace having to memorize formulas for multivariable chain rules in an arbitrary number of variables, right? Instead of sitting there and trying to rack your brain for what this formula was, you can just draw out this tree and then follow the branches, add them up, and then that's your multivariable chain rule. So let's see about 2 independent variables. So let's say we have z equals f of xy, but now x is some function of u and v, and y is some function of u and v, right? Or maybe I won't even write like g and h because I won't use them in the partial derivative notation, right? But I mean, I like indicating that it's a function, right? So maybe I will leave it. I'll use x and y in the partial derivative notation, but we do have that x and y are both functions of the variables u and v, right? And so what do we have now? Well, if we were to come up with a chain rule here, let's see what we would have. We would have our top node. So I'd like to save some room. I'd like to write. We have z equals f of xy, right? And then let's remember that x is a function of u and v, and y is a function of u and v. And remember, we start by making nodes, right? And so we start with the variable z, and then the variable z depends on the variables x and y. And then the variables y, x and y, depend on u and v. So this is u, this is v, this is u, this is v. And we have nodes, or we have branches on this tree, connecting all of the nodes here. And now we need to label each branch. And so for the first one, we're going from z to x. So that's the partial derivative of z with respect to x. And then once we're at the point x, we have two paths we can travel, or two branches we can go along. We can go along the branch from x to u, which is the branch partial x, partial u, or we can go along the branch from x to v, which is partial x, partial v. And then similarly, we had two choices at the very top of the tree. And now if we went down the y branch here, we would have partial z, partial y, right? And then once we're at y, we have two choices. We have partial y, partial u, and partial y, partial v. And how do we come up with our formulas for the multivariable chain rule? Well, notice there are two independent variables now. And so that means there are going to be two expressions. We're going to have partial u, excuse me. We're going to have partial z, partial u equals something. And then we're going to have partial z, partial v equals something else, right? So how do we find partial z, partial u? Well, we follow every branch that ends at the node, at a u node. So we follow every path that ends in the variable u. And so if we travel down the x branch, we're going to have partial z, partial x, and then we want to pick paths that end at the variable u. So this is times partial x, partial u. And then we want to go down the y branch and also end at a u node. So this is partial z, partial y. And then to get to u from y, I go down the branch partial y, partial u. Then I take this sum. And this is my formula for calculating partial z, partial u. This is one of the multivariable chain rule here. And so what do I have next? Now I want the same thing, but for the variable v, right? And so first, let's go down the x branch first. So I get dz del z del x. And then now I want to end at v nodes. So I go down the branch partial x, partial v this time. And then I want to go down the y branch and also end at a v node. So the first branch I go down is partial z, partial y. And then to get to the y node from y, I go down partial y, partial v. And this is my formula for dz dv of the multivariable chain rule. So this is multivariable chain rule for two independent variables. Okay, and so now we can generalize this, right? We can keep doing this. Like, well, what if our function f was a function of 3 variables, and then x and y were functions of 5 variables or something for like an arbitrary number of independent variables, right? So there is a generalized chain rule here. Okay. And so what we have is, let's consider w is a function of m variables, say x1 through xm. And for all I in the set, so let's say, and for all I in the set from 1 to m, we have that the variable x sub I is actually a variable, or is actually a function of n variables. So we could have, say, like ti or t1 up to tj, and then we end at like tn, where j is in the set 1 to n. Okay, and so what we have here is that f is a function of the variables x1, x2, x3, da da da, all the way up to xm, and then each xi, right, is a function of n variables. So like x1 is a function of t1, t2, all the way up to tn. x2 is a function of t1, t2, all the way up to tn, et cetera, et cetera, et cetera. And so w here is a function of m variables who each variable is in turn a function of n variables. Then, to find the partial derivative of w with respect to the ith variable, you take the following sum. It's partial with respect to w, or partial w partial x1 times partial x1 partial tj, right? And sorry, this is not the partial derivative with respect to the ith variable. It's partial derivative with respect to the jth t variable, right? So this should be partial derivative of w with respect to tj, right? And you'll have to do this for every j spanning from 1 to n. And so then plus dw, or partial w partial x2 times partial x2 partial tj plus et cetera, all the way up to partial dw partial x in, or m, excuse me, since there are m variables in the x, right? Partial xm partial tj. And so this is your generalized chain rule. And again, like memorizing this formula for an arbitrary number, for arbitrary numbers n and arbitrary number n, is a lot worse than drawing a tree, right? And so we can recover the generalized chain rule by drawing trees, which is pretty cool. So the last thing I want to say here is I want to give some formulas on implicit differentiation. So remember, an implicit function is usually given by f of xy equals 0, or you say y equals f of x implicitly, right? And what it means is, like, you could have something like x squared plus 3xy plus like 5y squared equals 0, like where it's pretty difficult to solve for y by itself, or in sometimes you have to express, like, you can't isolate y by itself, or if you do isolate one y by itself, like for example, what would we have here if we tried to solve this for y, right? So we would have 3x plus 5y times y equals negative x squared. And so we have y equals negative x squared over 3x plus 5y, right? And we have a y over here still. So we have y equals a function of x, but we still have y over here. And when we still have, like, when we can't write y explicitly in terms of x, like we still have to have y's on the right-hand side of the equation, well, then we say this is the implicit function, or y is a function of x implicitly, right? And so we can still calculate derivatives here, right? We can still find, like with this example, what if we wanted to find dy dx, right? Because like this is still a function and it still has a derivative, but it's expressed implicitly. And so how can we do that? Well, from Calc 1, what we would do is just take the derivative with respect to x of both sides. Well, the derivative of 0 is 0, right? And so maybe I'll come back up here just to stay on the same page. Okay, well then what we would do is we would get 2x plus, and then it's 3 times the derivative with respect to x of x times y plus 5 times the derivative with respect to x of y squared equals 0. And now that we're in the language or in the realm of multivariable calculus, you would want to say, well, oh, that derivative is 0, right? Like the derivative with respect to x of y squared is 0 since it's an independent, or since it's a constant with respect to x. But this is implicit differentiation, and y is a function of x. So its derivative is not 0 because y depends on x, right? You can express y in terms of x. And so what we'd get for this derivative is, when we take derivatives, well, you have x times y, and this is a product of functions, so you have to use the product rule, right? And so you get y plus x dy dx plus 5, and then this is going to be chain rule, right? So that's 2y dy dx equals 0. And what can we do now, right? Because we're solving for dy dx. So now that we know we're doing implicit differentiation here, and I'll copy our function. We have x squared plus 3xy plus 5y squared equals 0 is the function that we're trying to find dy dx for, right? And what can we do now? We have 2x plus 3y plus 3x dy dx plus 10y dy dx equals 0. And now we can just do some algebra, solve for dy dx. We get 3x plus 10y dy dx equals negative 2x minus 3y. So dy dx is negative 2x minus 3y all over 3x plus 10y, right? And here's an expression for dy dx. But again, it's implicit differentiation because our derivative is in terms of x and y, right? So the point of me bringing up implicit differentiation is that instead of going through all of this here, right, where it's like, okay, well, here's your function, you do single variable differentiation, then you do some algebra, and it can get like increasingly kind of tedious. We can use our knowledge of the multivariable chain rule to be able to calculate implicit derivatives simply using partial derivatives, right? So let's suppose we have z equals f of xy, defines y implicitly. Let's say implicitly as a function of x. Via setting it equal to 0, so the level curve at 0, right? Here we have f of xy equals 0. Then the implicit derivative dy dx is given by negative partial f partial x over partial f partial y. And so you can calculate dy dx by taking the partial derivatives and then throwing a negative into the numerator. And so let's see what we would have gotten here. If we have, so let's copy our function. It was x squared plus 3xy plus 5y squared was our function, right? And we'd set that equal to 0. Well, what's partial f partial x? It's 2x plus 3y, and then partial f partial y is 3x plus 10y. And so now by our formula, that's negative partial f partial x over partial f partial y, we get negative 2x minus 3y all over 3x plus 10y. And this is so much easier. We came to the same result much, much faster than strictly using single variable calculus. And so that's the point of this here. And this can be generalized as well. So if you were to, like, for 3 variables, say, like, if f of x, y, z equals 0 defines z implicitly as a function of x and y, then we can calculate del z del x is negative del f del x over del f del z, and del z del y is negative del f del y over del f del z. And so here's implicit partial differentiation when f is a function of 3 variables, and then we can get z defined implicitly as a function of 2 variables. And so this concludes our discussion of the multivariable chain rule and implicit differentiation. Next, we're going to return to vectors. We want to talk about directional derivatives and gradients, which is very much so based on a lot of the vector arithmetic that we've learned in the past.